Hello and good afternoon friends, welcome to CEC-UGC live lecture. Dear friends, as you know, in this session of ours, we usually try to bring for you the science subjects and all the related topics with which you have interest. So for the lovers of the chemistry, we would like to tell you that we are going to start a new series, and this series is Chemical Reactivity and Mechanism, and under this very series today we are going to discuss on carbocations, substitution and elimination. And for this we have with us in our studios Mrs. Vandana. She is Assistant Professor in Department of Chemistry, Dayal Singh College, Delhi University. So first of all, I would like to welcome our guest Mrs. Vandana, and I hope under her able guidance and her lecture we are going to learn more and more. So first of all, ma'am, welcome to the EduSet lecture, and I hope through you we are going to learn something new.
Thank you, Gitika. Good afternoon, everyone. In the lecture series of Chemical Reactivity and Mechanism, today I would like to explore more about the carbocations, nucleophilic substitution, elimination, and the difference between substitution and elimination. As we know, organic reactions takes place by radical or more commonly by ionic mechanism. What are reaction intermediates? The reaction pathway is influenced by stability of intermediate radicals or ions. The common reaction intermediates are carbocations, carbanions, free radicals, carbenes and nitrines. We are aware of it that carbocations and other intermediates are short-lived and quickly converted to more stable molecules. First of all, we talk about the carbocations. What is carbocation? It is an electron deficient carbon is bonded to 3 other atoms, uses sp2 orbitals. When we are talking about the stereochemistry of carbocation, sp2 orbitals lie in one plane and directed towards the corners of an equilateral triangle, and one empty p orbital is also there. So bond angle is 120 degree. Generation and fate of carbocations. Generation of carbocations can be discussed in 2 points. Number 1, a direct ionization in which a group attached to a carbon atom leaves with its pair of electrons. Number 2, a proton or other positive species adds to one atom of an unsaturated system, leaving the adjacent carbon atom with a positive charge. The reactions of carbocations. First, the 2 pathways. Number 1, the carbocation may combine with a species containing an electron pair, for example, halide ion, hydroxyl ion, or any other neutral ion. Number 2, the carbocation may lose a proton or much less often another positive ion from the adjacent carbon atom to give the alkene or olefin. 2 other pathways other than previous one in which carbocation reacts to give other carbocations are rearrangement and addition. In rearrangement, an alkyl or aryl group or a hydrogen migrates with its electron pair to the positive center, leaving another positive charge behind. You can see in the reaction that primary carbocation rearranges to secondary carbocation with the hydrogen shift. Addition, a carbocation may add to a double bond, generating a positive charge at a new position. Now we discuss the stability of carbocation. 3-degree carbocation is more stable than 2-degree carbocation and requires a lower activation energy for its formation. 2-degree carbocation is in turn more stable than a 1-degree carbocation. Methyl and 1-degree carbocations are so unstable that are never observed in solution. The stability of carbocations in alkyl groups bonded to the positively charged carbon are electron releasing and thereby delocalize the positive charge of the cation. Second, electron releasing ability of alkyl group can be explained by inductive effect and the hyperconjugation. First point, what is inductive effect? In the carbocation, the positively charged carbon polarizes electron of adjacent sigma bonds towards it. The positive charge on the carbon is thus localized over nearby atoms. The larger the volume over the positive charge is delocalized, the greater the stability of the carbocations. Hence, 3-degree carbocations are more stable than 2-degree, 2-degree carbocations are more stable than 1-degree, and 1-degree carbocations are more stable than methyl. What is hyperconjugation? Hyperconjugation involves basically the partial overlapping of sigma bonded orbital of an adjacent carbon hydrogen or carbon-carbon bond with the vacant 2 orbital of the cationic carbon. Hence, there is a delocalization of positive charge. When there is a delocalization of positive charge, the stability of the carbocation will be increased. You can see in the figure that dotted line shows the delocalization of electrons from an adjacent carbon hydrogen bond into the empty 2p orbital of the positively charged carbon, and the orbitals of these carbon hydrogen bonds which are perpendicular to the vacant 2 orbital of the cationic carbon cannot flow into the vacant 2p orbital and cannot participate in the hyperconjugation. What is reaction mechanism? Reaction mechanism has a stepwise reaction mechanism that explains it happens, that is how the product is formed from reactant step by step through intermediates. Organic reactions may be classified into the following categories. Number 1, substitution reactions, addition reactions, elimination reactions, and rearrangement reactions. Types of reactions you can see in the figure, that 1, substitution in which bromide ion is substituted by hydroxyl ion. Elimination, simple, H2O is eliminated to form double bond. Addition, bromine molecule adds to the double bond, and rearrangement, the position of double bond is changes. What are nucleophiles and electrophiles? Nucleophiles are electron rich. When they are electron rich, they are seeking nucleus and typically have a negative charge, we can say anions or a lone pair. The charged nucleophiles may be alkoxide ion, bromide ion, carbon ion or cyanide ion. Uncharged nucleophiles, or we can say neutral nucleophiles, are the nucleophiles having lone pair of electron like water molecule, primary amine or thiols. Electrophiles. Electrophiles are electron deficient, electron seeking reagent and typically have a positive charge or are polarizable molecules that can develop an electron deficient center. As nucleophiles, electrophiles are also charged or neutral species. Like charged electrophiles, we can say proton, carbocation or nitronium ion, and charged electrophiles. You can see that polarization is a sequence of atoms with different electronegativities. If there is a difference in electronegativities, there is a possibility of generation of electrophiles. What are leaving groups? Leaving groups is the terminology used for ions or neutral molecules that are displaced from a reactant as part of mechanistic sequence. Frequently, this displacement is the consequence of a nucleophile attacking an electrophile and where the electrophile carries a suitable leaving group. Good leaving groups are those that form stable ions or neutral nucleophiles after they leave the substrate. So, what is substitution reaction? A functional group in a particular chemical compound is replaced by another group. Organic substitution reactions are classified in several main organic reactions types depending on whether the reagent that brings about this substitution is considered as electrophile or a nucleophile or a reactive intermediate involved in the reaction is a carbocation, carbanion or free radical, or whether the substrate is aliphatic or aromatic. For example, photochemical chlorination of methane forming methyl chloride. So, we are having different types of substitution reaction. Number 1, nucleophilic substitution reaction in which attacking reagent is nucleophile. Electrophilic substitution reaction in which attacking reagent is electrophile, and third one is radical substitution in which attacking reagent is radical. Nucleophilic substitution reaction in which reagent is nucleophile. Depending upon the nature of the substrate, it may be aliphatic or it may be aromatic. We classify into different categories such as nucleophilic aliphatic substitution reaction, nucleophilic aromatic substitution reaction, and nucleophilic acyl in case of carboxylic acid group substitution, etc. The nucleophilic substitution can be produced by various mechanisms. Number 1, SN1, number 2, SN2, number 3, SNI. SN1 is monomolecular nucleophilic substitution. SN2 refers to bimolecular nucleophilic substitution. SNI, internal nucleophilic substitution. Nucleophilic reactions includes attacking reagent is nucleophile. Nucleophile replaces leaving group. Competing reaction may be elimination or may be rearrangement. Here are some nucleophilic substitution reaction. The main reaction is when a nucleophile attacks on methyl halide to give the methyl with nucleophile, means nucleophile is substituted the halide ion. You can see in the slide that when the nucleophile is hydroxyl ion, we get the product alcohol. When it is alkoxide ion, the product is an ether. When HS is there, a thiol is formed. RS negative is there, a sulfide is formed. Iodide is there, alkyl iodide is formed. Ammonia is there, an alkyl ammonium ion is formed. Water molecule is there, and alcohol will be the product. First of all, we will discuss about the bimolecular nucleophilic substitution. In this slide, you can see the mechanism of SN2 reaction. The hydroxyl ion as a nucleophile attacks on methyl bromide at the back side, and the intermediate is transition state, and the product is methyl alcohol. The attacking of hydroxyl ion and the leaving of bromide ion takes place simultaneously. So, intermediate is transition state. The rate of SN2 reaction depends upon 4 factors. Number 1, the nature of the substrate. Here we are taking alkyl halide. Number 2, the power of nucleophile, the ability of the leaving group to leave, and fourth number, the nature of the solvent in which reaction is occur. First of all, we will discuss the first point, the effect of nature of the substrate on SN2 reaction. Unhindered alkyl halides, those in which the back side of alpha carbon is not blocked, will react fastest in SN2 reaction. That is, methyl will react faster than 1 degree, 1 degree, then 2 degree, then 3 degree. While a methyl halide reacts quickly in SN2 reaction, a 3 degree does not react because of crowdedness. The backside of alpha carbon in a 3 degree alkyl halide is completely blocked. Second point, the effect of power of nucleophile on SN2 reaction. Better the nucleophile, faster the rate of SN2 reaction. The table show the relative power or various nucleophiles. The best nucleophiles are the best electron donors. Here the table shows the reactivity of nucleophiles and relative reactivity. Effect of nature of the leaving group on the rate of SN2 reactions. The leaving group usually has a negative charge. Groups which best stabilize a negative charge are the best leaving groups. That is, the weakest bases are the stable as anions are the best leaving groups. Weak bases are readily identified on the basis of pKb values. In the table you can see that iodide has a highest value of pKb, hence it is the best leaving group and is a non-basic. The hydroxyl group is a poor leaving group because hydroxide ion is a strong base. Effect of the nucleophile on rate of SN2 reactions. The alpha carbon in vinyl and aryl halides, as in 3 carbocations we have discussed earlier, that in 3 carbocations the backside position is completely blocked and is hindered. Similarly, in vinyls and aryl halides, the alkyl halide do not undergo SN2 reactions. The overlapping p orbitals that form the pi bonds in vinyl and aryl halides completely block the access of nucleophile to the backside of the alpha carbon atom. Effect of this solvent on the rate of SN2 reactions. Basically 3 types of organic solvents we are considering. Number 1, protic solvents which contain hydroxyl or ammonium groups. Protic solvents slow down SN2 reaction, we will discuss it later. Second point, polar aprotic solvents like acetone in which no proton is there, which contains strong dipoles but no hydroxyl or NH2 groups. Polar aprotic solvents speed up SN2 reactions. Non-polar solvents are hydrocarbons. SN2 reactions are relatively slow in non-polar solvents. First, we will discuss the protic solvents. Protic solvents, for example, we are taking water molecule, methyl alcohol, ethyl alcohol, acetic acid, etc. Cluster around the nucleophile. We can say it is solvated and lower its energy. When it lower the energy, it means it stabilizes it and reduce its reactivity via hydrogen bonding. You can see in the figure that halide anion is solvated by ROH. A solvated anion has reduced nucleophilicity, reduced reactivity and increased stability. A solvated nucleophile has difficulty hitting the carbon atom. Effect of this solvent we are continuing. Polar aprotic solvents solvate the cation, counter ion of the nucleophile but not the nucleophile. Examples include acetonitrile, CH3CN, acetone, dimethyl formamide, dimethyl sulfoxide, hexamethyl phosphoramide and dimethyl acetamide. Polar aprotic solvents solvate metal cations and leaving the anion counter ion bare and thus more reactive. You can see that acetonitrile is solvated around metal sodium. Effect of this solvent on the rate of SN2 reactions. Non-polar solvents like benzene, carbon tetrachloride, hexane do not solvate or stabilize nucleophiles. SN2 reactions are relatively slow in non-polar solvents similar to that in the protic solvents like benzene, you can see carbon tetrachloride and N-hexane. Next, nucleophilic substitution reaction SN1. SN1 means S for stands for substitution, and for nucleophilic first order, the rate depends on the concentration of only one reactant, that is why SN1, and not on the alkyl halide. The order of reactivity of substrate for SN1 reaction is the reverse of SN2, 3 degree, then 2 degree, then 1 degree, then vinyl, then phenyl, and then methyl. Here we are taking the example hydrolysis of tertiary butyl bromide when reacts with water to form tertiary butyl alcohol. The SN1 reaction completes in two steps. In first step, the carbocation is formed. In the second step, the nucleophile attacks on the carbocation and elimination of proton to yield the product. So, SN1 reaction is first order reaction and involves two steps. Mechanism of SN1 reaction. Mechanism of SN1 reaction, the slower rate limiting dissociation of the alkyl halide forming a carbocation intermediate, the rapid nucleophile attack on the carbocation. The rate of SN1 reaction depends on three factors. Number 1, nature of the substrate, ability of the leaving group to leave, and nature of the solvent. The rate is independent, it is very important point, the rate of SN1 reaction is independent of the power of the nucleophile, whereas in the SN2 reaction, the rate depends on the nucleophile also. Nature of the substrate on SN1 reaction, highly substituted alkyl halides form a more stable carbocation. You can see the tertiary carbocation will be more stable from secondary, secondary will be more stable than primary, and primary will be more stable than methyl. Stability of carbocations. Allyl and benzyl halides also react quickly by SN1 reactions because their carbocations are unusually stable. Why they are unusually stable? Because of delocalization over an extended pi system, delocalization of positive charge. You can see in the allyl carbocation there are two canonical forms, and in benzylic carbocation there are 4 canonical forms, and more canonical forms formed in the intermediate, more will be the stable of that particular intermediate. So, benzylic carbocation will be more stable than the allylic carbocation. Relative stability of all types of carbocations. Here we can see all types of carbocation like 3 degree benzylic, 2 degree benzylic, 1 degree benzylic, 3 degree allylic, 2 degree allylic, 1 degree allylic, then tertiary, secondary, primary, vinylic, phenylic and methyl carbocation. Here the important points are 1 allylic and 1 benzylic carbocations are about as stable as 2 degree alkyl carbocations. 2 degree allylic and 2 degree benzylic carbocations are about as stable as 3 degree alkyl carbocations. 3 degree allylic and 3 degree benzylic carbocations are more stable than 3 degree alkyl carbocations. Phenyl and vinyl carbocations are unstable. Hence, they do not undergo SN1 and SN2 reactions. Effect of nature of leaving group on SN1 reaction. The nature of leaving group has the same effect as on SN2 reactions. The better the leaving group, the faster carbocation can form, hence faster will be the SN1 reactions. The leaving group usually has a negative charge. Group which stabilize a negative charge are the best leaving group. That is, weakest bases are stable as anions and are the best leaving groups. Weak bases are readily identified. They have high pKb values, as we have already discussed in case of SN2. Effect of the solvent on SN1 reaction. The nucleophile is not involved in the rate determining step, so solvent effect on the nucleophile do not affect the rate of SN1 reactions. Polar solvents, both protic and aprotic, will solvate and stabilize the charge transition state, lowering the activation energy and accelerating the SN1 reaction. Non-polar solvents do not lower the activation energy and thus make SN1 reaction relatively slower. You can see the order, the relative rates of SN1 reaction due to solvent effects. Elimination reaction. Alkyl halide may react with basic nucleophiles such as NaOH, sodium hydroxide, via substitution reaction. Also recall our study of preparation of alkenes when 2 degree or 3 degree alkyl halide is treated with a strong base and NaOH, dehydrohalogenation occurs, produce an alkene and elimination reaction. You can see the bromocyclohexane when reacts with potassium hydroxide in ethanol, cyclohexene will formed, means there is a elimination reaction rather than substitution. Substitution and elimination reactions are often in competition. We shall consider the determining factors after studying the mechanism of elimination. Elimination reactions are of two types, E1 and E2. First we will discuss the E2 reaction mechanism. There are two kinds of elimination reaction, as we have told. E2 reactions occurs when 2 or 3 degree alkyl halide is treated with a strong bases such as hydroxyl, alkoxide, NH2, hydrogen, etc. All strong bases like hydroxide are good nucleophiles. In 2 degree and 3 degree alkyl halides, the carbon in the alkyl halide, which is alpha, will be hindered. In such cases, a strong base will abstract, or we can say remove, a hydrogen ion from the beta carbon. You can see from the reaction that hydroxyl ion abstract the beta hydrogen and before it hits the alpha carbon. Thus, strong bases causes elimination in 2 degree and 3 degree alkyl halides and cause substitution is in unhindered methyl and 1 degree alkyl halides. E2 mechanism. In E2 reactions, the base 2 hydrogen sigma bond formation, this carbon 2 hydrogen sigma bond breaking, the carbon 2 carbon pi bond formation, all these takes place simultaneously. Here no carbocation intermediate form. Reaction in which several steps occur simultaneously are known as concerted reactions. Jatsev rule, what it says? It says that in elimination of hydrogen halide from alkenes, more highly substituted alkene product will be formed. You can see that the 2 butene and 1 butene, the percentage of 2 butene, the highly substituted alkene will form in major amount. E2 reactions are anti-periplanar. E2 reactions do not follow Jatsev rule always. E2 elimination occur with anti-periplanar geometry. What is that? Periplanar means that all 4 reacting atoms, hydrogen, carbon, carbon and halide, all lie in the same plane. Anti means that hydrogen and halide, which has to eliminate, are on the opposite sides of the molecules. And look at the mechanism again and note the opposite side and same explain orientation of the mechanism. What is even reactions? Just as SN2 reactions are analogous to E2 reactions, so SN1 reactions have an analog even reaction. Even means elimination with unimolecular means first order reaction. The rate of reaction depends on only alkyl halide and not on the base. Even elimination, the substrate undergo slow heterolysis to form halide ion and a carbocation. In second step, carbocation rapidly loses a proton to the base and forms the alkene. Even in SN1 normally occur in competition. Whenever an alkyl halide is treated in a protic solvent with non-basic poor nucleophile. The best even substrate are also the best SN1 substrate. The mixture of products are usually obtained. As with the E2 reactions, even reaction also produce the more highly substituted alkene as we have discussed according to Jatsev rule. However, E2 reaction where no carbocation is produced, carbocation rearrangement can occur in even reaction. For example, when tertiary butyl chloride reacts with water in ethanol at 65 degrees Celsius, we will get tertiary butanol with methyl propene. In most unimolecular reaction, SN1 is favored over even, especially at low temperature. Such reactions with mixed product are not often used in synthetic chemistry. If even product is desired, it is better to use a strong base and force the E2 reaction. Note that increasing the strength of the nucleophile favors SN1 over E1. So basically, when we are talking about substitution or elimination, the main two things are nucleophilic power and the leaving ability. So we must understood the basic concept about the nucleophilic power and the leaving ability. We have to remember it. The basicity is a matter of equilibrium. Nucleophilic power and leaving ability are matter of rate. Of two bases, one is said to be stronger because at the equilibrium it holds a greater proportion of the acid. Of two nucleophiles, one is said to be more powerful because it attacks the carbon faster of two leaving groups. One is said to be the better because it leaves the carbon faster. Basicity involves interaction with proton, nucleophilic power and leaving ability involve interaction with the carbon. Substitution versus elimination. Many molecules, nucleophiles are also strong bases, for example, hydroxyl ion and alkoxide ion. The substitution, nucleophilic and elimination reaction often compete with each other on the basis of nucleophile nature and bases. The ratio of substitution nucleophilic and elimination products depend upon the relative rates of the two reactions. What favors elimination reactions? Attacking nucleophile is a strong and large base, steric crowding in the substrate, high temperature and low polarity of the solvent. So, when nucleophile attacks on the alkyl halide, nucleophilic substitution takes place, and when there is a beta elimination, alkene will be formed. Summary of substitution versus elimination for haloalkanes. For methyl and 1-degree haloalkanes, SN2, the only substitution reaction observed. SN1 reaction of methyl halide are never observed. The methyl cation is so unstable and it is never formed in this solution. With primary, the main reaction with strong bases such as hydroxyl and the ethoxide, also the main reaction with good nucleophile weak bases such as iodide and acetate anion. E2 कब होगा? When E2 will take place, the main reaction with strong bulky bases such as potassium tertiary butoxide. Primary cations are never formed in this solution, therefore SN1 and even reactions of primary halides are never observed. For 2 degree and 3 degree haloalkanes, secondary, the main reaction with weak base, good nucleophiles such as iodide and acetate anion SN2 will takes place. E2, the main reaction with strong bases, good nucleophiles such as hydroxide and CH3 CH2O negative. SN1 and E1 common in reactions with weak nucleophiles in polar protic solvents such as water, methanol and ethanol. Tertiary alkyl halide, the SN2 reactions of tertiary halides are never observed because of the extreme crowded around the 3 degree carbocation. E2, main reaction with strong bases such as hydroxide and alkoxide. SN1 and E1 main reactions with polar nucleophiles and weak bases. Now, how can we predict that particular mechanism will follow the substitution or elimination? So, we can predict the mechanism on the basis of the points. Number 1, non-basic good nucleophiles like bromide and iodide will cause substitution, not elimination. In 3 degree substrate, only SN1 is possible. In methyl and 1 degree substrate, SN2 is faster. For 2 degree substrate, the mechanism of substitution depends upon the solvent. Strong bases like hydroxide and alkoxide are also good nucleophiles. Substitution and elimination compete. In 3 degree and 2 degree alkyl halide, E2 is faster. In 1 degree and methyl alkyl halide, SN2 substitution will occur. Weak bases, weak nucleophiles like water molecule, ethanol, acetic acid, etc. cannot react unless a carbocation forms. This only occurs with 2 degree or 3 degree substrate. Once the carbocations forms, both SN1 and E1 occur in competition. The substitution product is usually predominant. Higher temperature increases the yield of elimination product over substitution. Elimination produces more product than substitution, hence greater the entropy or disorderness of the reaction. Polar solvents, both protic and aprotic, like water, methyl cyanide respectively, favor unimolecular reaction SN1 and it may be E1 by stabilizing the carbocation intermediate. Polar aprotic solvent enhance bimolecular reaction SN2 or E2 by activating the nucleophile. Hence, it is another table for predicting the reaction mechanism. When pKb value is 4.7, base is moderate and nucleophile is very good, the alkyl halide substrate with methyl undergo SN2 reaction. 1 degree alkyl halide undergo SN2 reaction. 3 degree undergo E2. 2 degree undergo SN2 reaction. When pKb value 6.0 say 7.0 and base is moderate, nucleophile is very good, the alkyl halide undergo SN2 reaction with methyl. 1 degree undergo SN2 reaction. 3 degree undergo E2. 2 degree undergo SN2 reaction. When pKb value is 9 and our base is weak and nucleophile is fair, the mechanism for methyl alkyl halide will undergo SN2 mechanism, 1 degree SN2 reaction, 3 degree E2, 2 degree E2, and with HCl, HBr, H hydrogen iodide are assumed to be in aqueous solution, a protic solvent. This alkyl halide with methyl undergo SN2 reaction, 1 degree SN2 reaction, 3 degree SN1 reaction and 2 degree undergoes SN1 reaction. So, basically on the basis of pKb values, basicity and nucleophilic nature, we can predict that the reaction will follow which type of substitution, SN1 or SN2, or which type of elimination, E1 and E2. So we come to conclude that the reaction proceed by substitution SN1 or SN2 or by elimination E1 or E2, means substitution or elimination always compete, and it depends on the nucleophilicity and basicity. Thank you.
Thank you, ma'am. Thank you so very much for delivering such a nice lecture. Now, I would like to ask some general questions. You talk about the carbocations, but basically the carbocations are?
Carbocations are the intermediates formed in the reactions. A reactant come to product via the intermediates. So, carbocation is one of the intermediate.
And this basically helps in further carrying out the reaction, chemical reactions?
Yes, more the stable of the carbocations, the priority to form a product is higher.
What are the basic other elements which are available for furtherizing the
reaction intermediates?
Exactly.
Other than carbocation, the most reaction intermediates are carbanion, carbenes and nitrines.
And what are these carbenes, nitrines? Please tell us in detail.
We will discuss in later in the coming series in a very explore manner carbenes, nitrines and carbanions. These are also intermediate form in a reactions through which a reaction proceed to the products.
And what are the other elements which are required for a general reaction to take place?
A reaction includes reactants. Reactants attacked by attacking reagent, proceed through intermediates and then come to the product. So, in reaction it depends on the reaction intermediate how much they are stable. The product will be more stable and the amount, the percentage of the product will be more if the intermediates are stable one.
Sometimes we have seen that during the chemical reaction, catalyst plays an important role. Does every reaction requires catalyst or only few reactions require catalyst?
As we have said that intermediates are unstable and we cannot isolate the reaction intermediates, but they are formed during the reactions. But what are catalysts? We need to add separately catalysts, they are unaffected in the reaction. This is the difference between catalyst and reaction intermediates. Catalyst you have to add in the reaction while intermediates are formed from the reagent plus attacking reagent.
Definitely. Ma'am, could you please give us any example describing about the reactants and the reagents and the intermediates? Could it be possible?
Okay. Like tertiary alkyl bromide, when react with potassium hydroxide, it will give tertiary butyl alcohol. So, tertiary butyl bromide is a reactant, potassium hydroxide is a attacking reagent, carbocation, tertiary carbocation is the reaction intermediate and the product is tertiary butyl alcohol.
Ma'am, could it be possible that if a reaction has taken place and after getting the content or the matter which come out after the reaction, would it be further go for other reaction?
No doubt, we have chain reactions, one reactant give second one product, then first product will use for another reaction. It always happens when we are seeing the chain reactions.
It is basically with the chain reactions.
Yes.
But are there any conditions where after getting the residue or the part, it loses its substantiality? It is not further useful for taking reactions further?
It is very rare that we will get 100% product. So, side products are there. First of all, we have to remove the side product, then only we can use the product and use for further reaction.
And when we talk about this, as per as our topic is chemical reactions and mechanism, we are basically talking about. So, what does mechanism signifies here?
If you know the mechanism of a reaction, you can increase the percentage amount of the product. For a reaction, it is very important. Not only in the laboratory, but more importantly in the industrial level. when you know the mechanism, you can increase the amount of product and reduce the side products. So mechanism has its own importance.
Mechanism has its own importance.
Yes.
But ma'am, if the ratio is not taken into account while carrying out a reaction, what are the after effects of the reaction, of that ratio which would not have been taken into a accurate amount?
There are so many factors affecting a reactions, as we have discussed the SN1 reaction, that SN2 reaction is affected by 4 factors and SN1 reaction is affected by 3 factors. So all factors are included to produce a product. So we cannot say that only depends on the one factor, we can say the product amount will be greater. We have to look after all the factors affecting a reaction.
Sometimes it is seen that for carrying a particular reaction, we require different temperatures. For example, a chemical reaction takes place in a high temperature. Sometimes a reaction does not require a temperature at all. It is highly reactive, that while attracting with the other compounds or elements, it reacts heavily. What is the reason behind that?
You are right, Gitika. Actually, the temperature, what it did, it will lower down the activation energy of a reactant, hence the product will form more, and that's it. Means it lower down the activation energy of the intermediates or reactants.
What precautions should be taken while all the students who might be watching us, while inside the laboratories we have seen that students playing with the reactants and without caring for the lives, they used to just carry out the reactions.
Okay. When you are doing any experiment in the laboratory, the basic requirement, you must wear the lab coat and always do the reaction in very small amount, because it is an experiment. You are just go through the reaction, you are not doing it for the purpose that you have to collect the product amount. So go for minimum amount, minimum solvent, because when you are throw down the chemicals into the sink, it hazard the environment. So always do in a very small amount.
That is the only
Yes.
precaution one could take while especially handling in the laboratory or carrying out any reaction. Does there is any reactant which does not react with any other compound or element?
Okay, like
If you talk about, is there any?
like cement, we barely use in the laboratory, because it reacts at very high temperature, like glass. Glass is also a chemical, so these are the
That is the reason that why the equipments in the laboratory are all made up of glass.
Yes, borosilicate glass commonly.
Even after giving the high temperature to them, they even don't blast. Sometimes it is
Yes,
seen
yes.
that a reaction require high temperature, but even then also the
Yes.
equipment does not blast, especially the tubes which we have for
Yes,
carrying
yes,
out
you are right,
experiments.
Gitika.
Ma'am, what about water? Because we
Okay.
have seen that sometimes water too has a reactivity with the other elements. What role does the water plays?
The main important quality of water is the pH of water, which is 7. Below 7 it will be acid, and above 7 it will be base. So water molecule has a pH of 7. It is the beauty of water that it can use for many purposes, almost for every purposes.
Okay, and ma'am, what basically this pH is? As you said that it defines that above 7 it is alkaline. No, it is acid, I am sorry.
What?
You talked about pH, that is the pH value. What basically this pH value is?
pH value is a parameter in which we calculate that pH of a particular solvent. If it is less than 7, then it will be acid. If the pH of a particular solvent is above 7, then it will be a base. And 7 it will be neutral.
Does there any other liquid components which do have pH value, or only water has its pH value?
All solvents have its own pH value, like acetic acid, as we are saying acetic acid. It has pH value less than 7. We are saying potassium hydroxide. It has pH value above 7. Every solvent has its own pH value.
Every solvent has its own pH value?
Yes.
Does the pH
You can easily measure from the pH.
does the pH value changes after adding some chemical?
Yes, pH value always changes. Even if you are standing a solvent, its pH value may vary depend on which particular solvent you are taking.
If we talk about the water alone, if we talk about the water is alkaline, for example of the seas, if we talk about it's a little sour, khara pani we used to call it, does it has a different pH value?
Not pH value exactly, some other metals are there, that is why we are saying it is salty water. Some salts are there.
So we can say that it differs with the help of the other metals or the solvents or the compounds elements present there.
It depends on the metals are which is included in that particular water.
Sometimes, ma'am, we have seen that if we talk about the things at the household level, that while cooking in aluminium kind of utensil, we see that if, for example, milk is there in that, does and the color changes, does it has any chemical reaction? Does the reactivity take place there? Or sometimes we have seen that we place pickles especially in a container or in a vase, which is not appropriate for keeping the pickles. Does there the reactivity take place?
Yes, some kind of reactions are there, like oxidation reduction reactions, acid base reactions are there, and this is the reason these particular reactions like acid base reaction and oxidation reduction reaction, the color like when you are having anything in the copper. So it depends from the electrochemical series that which element will reduce the another one. We can predict from the electrochemical series.
From the electrochemical series, we can predict their acidity and
the nature of reactions.
The nature of reactions.
What element will reduce which element and which element will oxidize the another. We can predict from the electrochemical series.
Electrochemical series. If we talk about the all the elements above in the series, they are basically.
Actually, there is a oxidation reduction potential. I don't remember right now, but on this basis we can explain that in which container you should proceed for which kind of reaction.
For which kind of reaction?
Yes. Oxidation reduction potential.
Ma'am, we are carrying this series on chemical reaction mechanisms. What else are we going to study in future more under this?
Actually, today we were discussing about carbocation. In next lecture of this series, we will discuss about the carbanion and its related reactions.
Its related reactions, and I would like to tell all the students who might be watching us right now that Mrs. Vandana would be tomorrow with us again, and under this series only, we'll try to understand more new concepts. And with this note, we would like to take your leave. Thank you so very much, ma'am, for being with us in this EduSet lecture. Thank you.